Hello, I'm Mathieu Bonneau and I'm going to present you a project I work on with Julian Martin, Nathalie Perard, Leroy Rogers, Christina Romagosa, and Fred Johnson. It's a joint work with the Department of Wildlife Ecology and Conservation of the University of Florida, Gainesville, the USGS Wetland and Aquatic Research Center in Gainesville, South Florida Water Management District in Palm Beach, and the French National Institute of Agronomic Research. In this presentation, I'll give you an overview of the cases where our method can be useful. If you already know in which cases you can use this method, you can directly go forward at 6 minutes and 30 seconds. We are considering the case where we have to monitor an entire landscape and try to control the spread of an invasive species. We will consider a toy example of a small island in the Caribbean where we have to search for an invasive species and remove it when found. First, we hypothesize that we have some information of where the species is present and not present. This information can come from monitoring of a dedicated staff, or it can also come from public records. In our example, we will consider that we have access to a plane and that we are able to fly all over the entire island trying to detect the species. Basically, our work consists in removing the species everywhere it's present on the island, but unfortunately, this will take too much time and money in practice. We consider that we have a dedicated budget for searching the invasive and removing it. This budget can be, for example, staff cumulated time, and we recognize that searching and removing the species take a certain amount of time. And we want to prioritize the land exploration regarding our time budget constraints. Let's start to describe the observations that we have. As in many applications, our observations are defined on a grid. Here is an example where our study area is divided into 36 sites. We use a small grid to simplify our presentation, but hopefully, in practical applications, a grid with a much higher resolution can be used. In our case, we flew over each site trying to detect the invasive tree. We thus have binary observations, species seen and species not seen. The problem is that your observations are not perfect due to observation error during the monitoring process. There is two types of error. The first one is a false positive error. It happens when you mixed up with another species. During the monitoring, you thought it was the invasive species that you were looking for, but in reality it was another one. This is the false positive error. The second type of error is a false negative observation. It happens when you miss the invasive species you were looking at. In this case, you did not record the presence of the species, although it was present in reality. It might not take the same amount of time to go on the different sites of the study area.
Environmental
First,
factors,
accessing to some sites might be
altitude,
very
or
complicated.
maybe
This is, for example, the case when there is no roads that drive to the
you can
site.
find on these sites.
The type of vegetation
basically
or
you
the
can
type of
also
land
have
can
access
also
problem.
influence the time
Some
needed to
sites
search for
can
the
be
species
very
on a site.
isolated.
We will differentiate between two types of costs. The first one is the search cost. It is the cost associated to the action of moving to the site and searching for the invasive species. The second type of cost is the destroy cost. Once you are on the site and the species is present, it is the cost associated with the action of removing the species from the site. Now that you have an intuition of what the method is designed for, I'll give you an overview of the mathematics behind the method. First, we propose to use hidden Markov random field to link the observation to a model of the spatial distribution of the species. This model has three parameters. The first two parameters, alpha and beta, are linked to the spatial distribution of the species. The third parameter, theta, is linked to the false positive and false negative error rate. Once the model parameters are estimated, we use the model to compute the probabilities that the species is present on a site, given our observations. These probabilities can be viewed as an updated version of the binary observations. Indeed, with our observations, the species is either present or not present, nothing more. With the probabilities, we have the likelihood of the species being present, thus bringing some sense of the uncertainty that we have on a particular site. To give you an example, let's consider the case where the species has been detected in all of this square area, but in the site in the middle. It is of course possible that the tree is not present on the site in the middle, but because the tree is present all around, it also gives us an intuition that we might simply have missed the tree. In this situation, if we only consider the observations, there is nothing on the middle site. There is no room for intuition or doubt. On the contrary, it is very likely that the probability of the species being present on the middle site will be higher than 0 due to the presence of the tree in all the neighborhood. Finally, what we want is to optimize our displacement. We want to maximize the number of visited sites where the species is present, or in other words, we want to minimize the number of visited sites where the species was not present. Our method proposes to maximize the expected number of visited sites where the species is present, given the observations, the search and destroy cost of each site, and our budget. The output of our method is simply a list of sites to visit. The optimization procedure is based on integral linear programming. With overview of in which case we can use our method, I will show you how to compute the sites to visit using MATLAB. So the first thing that you have to do is to give site number to each site of your study area. So one constraint that you have working with MATLAB is that we need to consider rectangular study area. So here basically in red, it's all the sites that are really in the study area, and in white are the sites that are outside of the study area. It's kind of a fake site, but they are here to make the study area rectangular. So you also have to note that the numbering of the sites is in the column direction. So the first site have to be the one on the top left corner, and the second is the one above, and so on. So now that we know that, the input of our algorithm have to be a CSV or an Excel file. This file should have 4 columns. So the first one is just the number of the sites that are inside the study area. So here basically it's just the number of the red sites. The second column is our observation. Here we can read that the tree was not observed on site number 4, but it was observed on site number 10. The third column is about the cost of searching the species on the particular site. Here, for example, it cost 46 to go and search for the species on site number 4. And the last column is the destroy cost. And here we can read that it cost 40 to remove the species on site number 8. So this is how should be set up the input of our algorithm. So now you can run MATLAB, so you have to open the GUI Melaleuca function. So this graphical interface will pop up, and you have several parameters to enter. So the first one is the number of rows of your rectangular study area. So for us, it's 6 rows and 6 columns. Then you have to define a budget. So here, for this example, let's try 300. And the rest of the parameters here are all for the parameters that will estimate the parameters of the hidden Markov random field. So to do that, we use the expectation maximization algorithm, which I will call the EM algorithm. So the EM algorithm needs some initial value to start. So here you have to initialize all the value of your hidden Markov random field model. So you have the 2 value for the alpha, 1 value for beta, and 2 values for theta. Here you have your false positive first and your false negative rate in second. So note that for alpha and theta you have 2 values to enter. You have to enter them between square brackets and separate the values with a comma. Finally, you have 3 more parameters. So what we propose to do is to run the EM algorithm several times. So here 5 times. So more precisely, the EM algorithm is run a first time using this initial value. It will then estimate new parameters, and these parameters will be used to initialize another run of the EM algorithm. So here basically with n test equal to 5, we will run 5 times the EM algorithm to estimate the parameters. So max iter is the maximal number of iterations that the EM algorithm is allowed to do. The more you will allow iteration, and the more the algorithm is likely to converge. So basically here we don't have a lot of variables, so we can increase this value. So here it really depends on your computer and the size of your problem. If you have a small problem or very good computer, you can try to increase this value, but if the value is too high, it might take really too long to compute the optimal solution. And heat is again parameters for the EM algorithm, and it's a number of iteration of the Gibbs sampling algorithm. And you will find all the details of these parameters in the article. So here again, we can increase it, and note that if you're not sure about what you have to put in some of the box, you can just click the help button and you will have a small description of the variable. So finally, we have to put the name of our data file. So here it's just data.csv, and we have to give the method some output file name. So here's a list of sites to visit will be saved in the file test.csv, and then we can run the method. We can see that the parameter estimation algorithm is running first, and we will see that it runs for 5 times. So here's what you get when the algorithm is done. You will have 4 figures. The first one here is the observations. So in gray, it's all the sites that are not inside the study area. In white is the sites where the species was not detected, and in black is the sites where the species was detected. You also have the cost, with the dark red sites being the site with the higher searching plus destroy cost. And here is what is computed from the algorithm. It's marginal probability. So basically it's the probability of having the species on each of the sites, and the probability is squared on a gray square. So the dark black sites are the site where the probability of having the species is close to 1. White sites are the site where the probability of having the species is equal to 0. So the first interesting thing is that in this case, and it's really not always the case, it depends on the spatial structure of the observation, but here there is no false positive observation. At least this is what estimated the EM algorithm. So we can see that the observation here are in dark black, meaning that there is no uncertainty. Where we saw the species is estimated as present. But the information that we have in addition is where the species was not detected. And here we can see that because we have 2 neighbors where the species was detected, we have, according to the algorithm, a high chance to see the species here. Same for these 2 sites here. Okay, and the aim of this algorithm is to combine this additional information with the cost and decide where to go for searching and removing the species. So here's the red sites as a site where the algorithm is telling you to go for searching for the species. The first thing that we can see is that, for example, this site here, which is this site, it's really not expensive to visit these sites, but actually the species was not observed here. And this is what this algorithm is about. Here we have a small probability that the species is present and a small cost. So instead of visiting only the sites, for example, this one, where we observe the species, okay, this one, the species is observed, but it has a really high cost. So this one, actually, if we visit this site, it's gonna cost you a lot in our budget, and only a small number of sites will be visited after. So as we can see, the algorithm say do not visit this one, but you can, on the contrary, go on this site with a really low search and discovery cost. I hope this video helps you to use our methods, and you are really welcome to send us an email if you have any additional questions.